So once you're comfortable working with points, lines, and surfaces, Rhino also deals with solids. These are very important to learn how to deal with and to make sure you are working with solids as opposed to just surfaces, because it allows you another entire suite of tools to deal with the geometries and create new geometries. For example, let's start by just making a quick box. Doesn't matter what size it is. Okay, I'm going to jump into my shaded mode here so we can see the box. I'm also just going to maximize the viewport. Alright, so if we orbit around this box, we can see that it's a closed box. There are distinct regions between what's outside and what's inside. And this box is actually made of 6 surfaces that are planes, and those edges are joined, just like you can join curves and other surfaces automatically using the box tool to create the primitive. And so when Rhino sees an object like this, where every edge is sealed and every face is closed, and it can create, or it can reconcile rather, an outside of the object versus an inside, that's what Rhino describes as a boundary representation or a solid. So it has to fully describe the boundary of some space that bifurcates the sort of inside of that shape and the outside of the world. And once it knows that, and you can see it here, it says closed extrusion. Sometimes it'll say closed polysurface as well. But if it says closed in the properties panel up here for your object, then it knows that it is fully closed and that there's an inside and an outside. And once you do that, you can begin to interact with it with a couple other tools in some other new ways. So the very first one of those that I want you all to be familiar with is these things called Boolean operators. And Boolean operators solve events, basically conditional events based on the intersections between two objects, or when two objects intersect. It deals with how to resolve that intersection based on what you say. So what we need to do here is actually create a couple other objects. So I'm going to just get a little fun here. I'm going to make a sphere, and that sphere should intersect with the cube or the box that we've made earlier. I'm going to do the same with a cone down here. All right, that should be plenty. So now that we have these, and you should notice, if we click on these, the cone here in our properties window says closed polysurface, and the sphere says closed surface. So when all of the sort of objects that we're reconciling their intersections through Boolean operations are solid, are closed, all of those operations will work. If they're not closed, if one of them is open, you'll get unexpected results. So whenever you're going to use these tools, make sure that whatever you're using is closed. Just to give you an idea of how to close open objects or to know whether or not they're open, if I say explode this surface into 6 surfaces, if I grab one of these, you can see a regular surface is an open surface. If I remove the top of the box, and then I take those remaining surfaces and I join them back up together, you can still say it's got an open surface. We can also check this by using a command called show edges. A surface or an edge to a surface that's open is typically called a naked edge. So like if we use this box, if we get rid of our edge analysis tool and we type show edges again, you can see that there are no naked edges found on our closed box. But if we add this guy, we can see described in pink here on the edge analysis tool that we have 4 naked edges. So anytime you have a naked edge, your Boolean objects or your Boolean operands are not going to work. So the Boolean tools are here in this, what's I believe called the solid tools rollout. It's represented by these 2 spheres intersecting one another. And so the very first things here are all of our different Boolean tool types. We have union, we have difference, we have intersection, and we have split. These are all pretty obvious. If I grab all of these things and I type in a Boolean union, it's going to turn it all into one big object. I'm going to undo that. What I'm actually going to do here is make several copies of this assemblage objects so that we can test a few different versions. So again, what I'm going to do with this guy is I'm going to type in Boolean union. I'm going to select the surfaces to union, and it creates a union. You can see that what it does is produce a seam in between. Now, if we move to a ghosted viewport, you can also see that it removes any geometry that's inside inside any other of these things. So the part of the cube that exists inside the region of the sphere is gone, the part of the sphere that exists inside the region of the cube is gone, and the same with the cone and its relationship to the cube. If you don't Boolean, you can see through this like little bit lighter zone here that there are contiguous representations of boundaries, or so interiors are contiguous with other interiors. And that's actually what Rhino is doing. It's like understanding when the air of two shapes is coincident with one another, and then it's removing that in order to create a union. Similarly, well, we'll go to the second one here. If you type in Boolean difference, it's going to ask for surfaces to subtract from. So the subtract D, or the subtract E. And then if we hit enter to continue, it's going to ask you the surfaces to subtract with, or the subtractors. So we're going to grab both of these guys. It's going to give you this option whether or not you want to delete your inputs, delete the subtractors. Right now we'll put it to yes. You can decide whether or not you do that. And boom, it's going to cut a cone-shaped void and a sphere-shaped void into our cube. It's pretty nice looking little form there. You can begin to see how useful this tool is. Similarly, the Boolean intersection will ask for a first set and a second set, and what it will do is only leave what remains. So what was turned into a void in the difference is actually left as a figure in the intersection. Boolean split, I'm actually going to delete this cone and just show us with the sphere. If we grab these two objects and we type in Boolean split, if we type in Boolean split before selecting objects, it'll ask us what to split. We can split the cube, we can cut it with the sphere. You can see the sphere remains, and we get this, and we get this. If you go backwards, start with the sphere, Boolean split, select the cutting surface, this guy, we've got a cut sphere, we've got that, and the box is unaffected because it's the thing that did the cutting, not the thing that got cut. That rounds out Boolean operators. There are some other really interesting solid tools that you can look for in here. One that I always find interesting and that sometimes students don't know, although it's becoming a much more popular tool, is that when you take two objects that have coplanar faces and Boolean union them, you can see there's this sort of trace of the Boolean operation here, these edges that exist even though they're on coplanar faces. You can use a tool called merge all faces, and it will get rid of those coincident edges and clean the model up. It's just really a kind of best practices thing here. And while we're over here, I'm going to zoom to selected to this guy. I'm going to turn us back to shaded mode so we're not seeing what's inside. Some other really awesome commands that we can cover are fillet edge. It's going to ask us for a radius of that edge. Let's see, how big is our radius? That's very small. You can see it creates that. Let's go for a bigger radius. Let's go for 3. Let's grab this thing. I think you can even probably adjust the radius of one side to the other. Then you get what's called a variable radius fillet by adjusting those handles. So if we click again, and when we want to select our edges to fillet, we want to hit enter or spacebar, then what it gives us is this sort of handle tool. And if we can go back and make this as big as we can, boom, we've got really cool filleted edges. All of a sudden, this shape is sort of inflected in a bunch of really, really interesting ways. We can go around it. There are also chamfers, which is the same as a fillet, except there's no radius. It softens the corner that way. There are some other weird ones in here. Create a solid from a bunch of overlaid planes. Oh yeah, shell we'll get to in a minute. There are things called wire cut. There are things called round holes or placing holes. Those typically relate to other disciplines. But you might look into them and discover them now when you're exploring with some of these techniques. The last one that I do want to show you guys is shell. So if we take any closed polysurface and we type in shell, it's going to ask us faces to remove from the closed polysurface and for a thickness. Let's change our thickness to 3 just to describe it here, and select faces to remove from the closed polysurface. Let's choose the top of the box for now, and you can see it's actually gone through and left us a 5-sided open box, and it's given that a uniform thickness all the way through. So we can, if we grab a little clipping plane here, we can see that it's given that infinitely thin box a thickness, which is very useful for describing things of material. The shell tool can be used in a bunch of different ways. You don't have to just use it to open the box. If you grab more faces, like if I grab 1, 2, and 3 faces, it's going to do that. Very useful. If you do this and this, it's going to make it into a little tube. Awesome. Lots of fun stuff. Feel free to explore with some of these solid tools, find some new ones. There are also some other really interesting ones in the surface manipulation tools that might be of interest to all of you. Please poke around and label what it is that you're doing. Keep track of the techniques that you're learning.